introduce Professor Michael Drmota, who talk about distribution properties of subsequences of automatic sequence. So please.
Okay, thank you very much. So first of all, I don't want to forget to thank the organizers to give me the opportunity to speak here. It's the first time for me being in Rio, and I enjoyed it really very much. Thanks for your great hospitality. And my talk, as I was already announced, is on distribution properties of subsequence of automatic sequences. So it's a topic where my colleagues and I have been working to the last few years quite a lot. So Christian Maudoy, Joël Reva, Jean-Marc Dessoyer, and others. And I want to present here more or less a survey on what we can do. And I will start with something that you certainly know, and I think it really doesn't need an introduction, but it's a very prominent sequence, a two-amorph sequence, as an example where everything starts more or less, and also the Rudin-Shapiro sequence. They are examples of automatic sequences that I want to present next. And then I will go to the subject, into the subject to subsequences of the two-amorph sequence. In particular, we are interested in subsequences where where this subsequence really gets generic or random. So we are interested in results where this subsequence is a normal sequence, in the sense that every block appears with its right frequency. Well, and then I will give you some hints which are what technical estimates are used to prove results like that. And finally, I want to go into the history in some sense, not only into the history, but to some backgrounds of these kind of programs. The first is to the Gelfond's problem that have been, in some sense, a starting point of this kind of subject. And as a second background subject is the Sana conjecture, and I will also present you some recent results on the Sana conjecture related to automatic sequences. Well, the two-amorph sequence has many definitions. You know probably more than me. So the easiest definition is the following one, at least from my point of view, that you start with 0, or it's a two-letter sequence, and then you repeat this initial sequence but reversing it. So 0 gets to 1, and then you repeat this but reverse, so 0, 1 gets to 1, 0, and the next will be 1, 0, 0, 1, and so on and so forth. And this is the two-amorph sequence, and this is the formal definition of that. And it's easy to see that this is the same as if you take the binary sum of digits modulo 2. The binary sum of digits refers to the usual q-adic expansion, so where q equals 2, and the sum of digits is just the sum of digits. So in the binary case, it's just the number of powers of 2 that you need to represent n. And there are other definitions, for example, this divide and conquer recurrence. And looking at this divide and conquer recurrence, you immediately observe that if you take two consecutive elements of the two-amorph sequence, or an even and an odd instance, then if one is 0, then the other will be 1, and so on and so forth. So which means that zeros and ones will certainly appear with the same frequency. And the two-amorph sequence has many other properties. So I only mention a few of them. So for example, that its subword complexity is linear bounded. So the subword complexity is the number of different consecutive blocks of length k that appear. And this pk is bounded by a constant times k. So it means that some consecutive block will not appear. So the maximal complexity is 2 to the k, of course. And in the two-amorph case, for example, you will never see 3 consecutive series in a row, for example. So it's cubeless. This is one instead of cubeless. So, and this also implies that this topological entropy of the related dynamical system. You take all shifts and take the closure, and the shift is of course then the transform there. Then the logarithmic, then the topological entropy is of course 0, because log p is logarithmic of logarithmic close divided by k, and it goes to 0. And all linear subsequences have the same properties, and all of them are automatic. So what is an automatic sequence? Or in this example, it's very easy to see which kind of automaton generates the two-Morse sequence. So here is an automaton that generates the two-Morse sequence. It has two states, some initial state, and then at every state you have two arrows. One is labeled with 0 and one is labeled with 1. And depending on the input, you choose either this or the other arrow. And the input is just the binary expansion of an integer n. So if you see a 0, then you stay. And if you see a 1, you skip to change the state. So this means that if you have an even number of 1s in the expansion, you come back to your initial state. And if you have an odd number of 1s, you go to the other state. So this two-Morse sequence is just generated by this automaton. Another very famous sequence is the Rudin-Shapiro sequence. And this is the Rudin-Shapiro sequence. And it can be described in different ways, for example, by a divide and conquer recurrence, or again, explicitly in terms of the binary expansion. But here you see that it's different, a little bit different from the two-Morse sequence. Here you see that you just add products of the i's and the I plus first digit. And this means that you only add a 1 here if these both are 1. So this means that you are counting the number of blocks of the form 1, 1 that appear. So it's the number of 1, 1 blocks mod 2. So this is another kind of relation to the binary expansion. And it's also an automatic sequence. And here is the minimal automaton that generates the Rudin-Shapiro sequence. It has 4 states. Well, and in general, what is an automatic sequence? It's an automatic sequence, or more precisely, a Q-automatic sequence, if it's generated by some kind of finite automaton where the input is the Q area expansion of n. So in the first two examples was the binary expansion, so it was Q was 2. So and here is we have 3 states, but the number of states could be different from Q, of course. So it is just a coincidence. So this is automaton, and I would explain it again how it works. So you have here Q equals 3. So you have 3 arrows from each state to some other states labeled with 0, 1, and 2. And for example, if you have an input 32, which has the expansion 1, 0, 1, 2 in base 3, then you start with the initial state, and then according to the digits, you go through the automaton. So 1, 0, 1, 2. And you end up in the state 2, and the output is some functional on the state, so it will be A in this case. And if you have another input, you do the same thing, and you will end up, in this example, in state 3 with the output B. And if you do it for all kind of inputs, then you get an automatic sequence. So formally, you can also generate this sequence with the transition matrices. So you have of course, it's a graph. If you consider only the edges that are labeled by 0, you have a graph. It has an adjacency matrix. It's also called a transition matrix according to the digit 0. Then you have a matrix according to the digit 1 and to the digit 2. And if you want to see the dynamics on the automaton, you can also just multiply these matrices according to the digits. So if you have the number 32 in base 3, it's 1, 0, 1, 2. You just have to multiply these matrices according to these digits, so M1, M0, M1, M2, applied to the unit vector 1, 0, 0, and you end up another unit vector. This will be the second unit vector, so this is it's according to the final state. So you can write an automatic sequence in the following form. You take this product of matrices according to the quadratic expansion, multiply it to the first unit vector, and take any function on it, and this is another kind of representation of an automatic sequence. And there are many, many examples. So we have seen the binary, so the binary sum of digits function mod 2, but of course you can take any sum of digits function mod m, or any so-called Q additive functions. For example, if you want to just count the digit 5 in the whatever, in the in the expansion to base 7 or whatever, then it's a Q additive function, and mod m, this is an automatic sequence. And you can also consider block additive function, like in the Rudin-Shapiro case, where you look at the block and you count, for example, blocks or whatever. What is common to all these sequences is that the output letters have a density or a logarithmic density. So, for example, in the two-Morse sequence, the output letters 0 and 1 both had the frequency 1/2, asymptotic frequency, and in general, it will an automatic sequence only has a logarithmic density, but under very mild conditions, for example, if the sum of these transition matrices is primitive, then you will have a density, like in the two-Morse case. Well, and all these automatic sequences have a linear subword complexity, so they will not be random or something like this. So they don't look random, they are very deterministic, and the dynamical system that are associated to all these automatic sequences have 0 entropy. But we are not interested in the whole sequence, but we are interested into subsequences. And the idea is that we use subsequences that have this, where the letters on the subsequence have the same asymptotic frequency, and it will turn out that this is very frequent case, as we'll see in a moment. And then it's also assumed that the gaps bit of the subsequence that we consider are increasing in some form, which means that we are losing memory more and more, and so that we have well, we can expect that this kind of subsequence will get random properties. It's, for example, if we take just a linear subsequence, or according to along a linear sequence, then we again have an automatic sequence, so we cannot expect any kind of random properties or pseudo-random properties. Well, as we see, for example, in two-Morse sequence, it has been already observed by Gelfand in '68 that if you consider a linear subsequence of the two-Morse sequence, then the letters will have the same asymptotic frequency as the original one, so zeros and ones will appear with the same frequency. In this example, it doesn't look like that, but it turns out that it's true. And it works for all linear subsequences. So this is not what we want to consider. So this is clear. It's again an automatic sequence. Everything is known about that. It gets more interesting, for example, if we consider Piatetsky-Shapiro sequence, so the integer part of n to the c, where c is larger than 1. So here is an example of that. And it turns out that if c is not too big, so it's expected that that this property holds for all non-integer c, but it could be proved by Mauduit and Rivard in 2 papers, and recently by Lukas Spielhofer, that up to c equals to 1.5, if you consider the two amorphous sequence along this subsequence n to the c, that the digits 0 and 1 will appear with the same frequency. So this is the first observation, and we will see more observation of that kind. So what is maybe most interesting are the primes. If you take the subsequence according to the primes, so the second, third, fifth, seventh, and so on, sequence of the two amorphous sequence, element of the two amorphous sequence, then it was proved by Mauduit and Rivard a few years ago that zeros and 1 appear with the same frequency. Actually, this was one of the conjectures that Gelfand formulated in this paper from '68. And actually, I think it was a major progress in this field as well. And this property is, of course, also related to the Sarnak conjecture. And Joël will speak on this topic tomorrow in more detail. What we have also worked on is the subsequence along squares. Of course, this is also related to a question of Gelfand. So Gelfand conjectured that if you take any integer polynomial and if you take the subsequence along this integer polynomial, then you should get the same asymptotic frequency. Up to now, it's known that it's true for squares. So this was also a paper by Mauduit and Rivard a few years ago. So that you consider this subsequence that the asymptotic frequency of the letters 0 and 1 are 1/2. And as I mentioned before, it all has been conjectured by Gelfand. And together with Jean-Marc Dessoulier and Morgenbesser, we considered now general automata. The idea is now to get these properties for automata. Well, we could not do all cases, but there are some cases that we could do. For example, the following one. If we consider an arbitrary automatic sequence along the Piasecki-Shapiro sequence n to the c, then it turns out that the density of the output letter is almost the same as the density of the original sequence. This works for all automatic sequences. Well, this generalizes a result of Mauduit and Rivard. Actually, we use part of their methods there. But this is a very general result, and it cannot be expected that it works for primes and so on. Actually, it's not true for primes and squares, but we can only show it for some special automata. Well, what can we do with squares and primes? It turns out that under some conditions, and the conditions that we considered are the following: one, that these transition matrices are not arbitrary, but invertible. So this is a very special situation, but it applies, for example, for the two amorphous sequence. So in this invertible situation, that if you take an automaton that is which is property and the automatic sequence that is generated by this invertible automaton, then it can be shown that if you take the subsequences along the squares and on the primes, that these densities exist. You can compute these densities, and it's not necessarily the same as of the original sequence. But you can determine them, and they exist. And if you take block additive functions, so they are not invertible, so usually it's not generated. For example, the Rudin-Shapiro sequence is a block additive function because you only consider the number of 1-1 blocks in the mod 2. This is not generated by an automaton where the transition matrices are invertible, but anyway, it can be proved that if you take block additive functions mod m, then the density along the squares and the primes again exists. So, for example, for the Rudin-Shapiro sequence, this works. This was proved by Mauduit and Rivard, and generalized now by a student of mine to general block additive functions. But this was only the first case, say. So we are not only interested in the appearance of the digits on the frequency, but we want to prove also more random properties. And it was a conjecture by Alouche and Shellit that the subword complexity of the two-Morse sequence along the squares is full, so that if you take this subsequence along the squares, that you get all possible substrings of length k, so which, in other words, that the subword complexity is 2 to the k. This was proved by Moshe in 2007, but without giving any quantitative result. So the question remained, what is the frequency of a given block? So, and of course, the most interesting case would be, or if this frequency is the generic one, so if you have a block of length k that appears with frequency 1 over 2 to the k. And in this case, a sequence is called normal. And there are only few known explicit examples of normal sequences, for example, the Champernowne sequence. And in a recent paper, together with Moderi and Rivard, we actually could prove that if we take the two-Morse sequence along the squares, that you get a normal sequence. So that gives you a more precise result on these subword complexities. You get the asymptotic frequency. It's always positive, and it's that's what you should expect. So this is quite interesting, at least from our point of view, so that you start with a sequence that has no random properties at all, so it's very rigid. So, and if you take a proper subsequence, for example, the squares, you get a normal one. And it turned out that this phenomenon occurs quite frequently. So Spiegelhofer and Müllner, so Spiegelhofer was a previous student of mine and Müllner is a PhD student of mine, actually they could prove that if you take the two-Morse sequence along the Piatowski-Shapiro sequence n to the c, where c is between 1 and 3/2, that it is also normal. Okay, so it seems that if you take an automatic sequence and take it along some sequence of this kind, that you should get some random or quasi-random property, maybe not in all cases, but in generic cases. And it can be proved also for block additive function mod m, so including the Rudin-Shapiro sequence. So the Rudin-Shapiro sequence along squares and also along n to the c, but not up to 3 over 2, but up to 4 over 3 is also normal. So it's a quite frequent phenomenon. And now I want to spend a few minutes on the proof techniques that we are using, not the whole proof, but one special instance, namely we need some free estimates, so of some special free terms, and they are related to the digital expansions. So I only do the binary case, and what we need here is a restricted sum of digits functions. So we don't count all the digits, but only the digits up to some level, say lambda. So we skip the higher order digits. We only take the first lambda digits. And of course, then this function gets periodic with period 2 to the lambda. And if you have a periodic sequence, you can do some Fourier analysis, and the terms that we really get are the following, that we consider the mapping n maps to e, where e is the exponential function on the unit circle, e to the alpha times this restricted sum of digits function, where this q has to be 2. So, of course, this function is then again periodic, and f lambda with capital F is now just a discrete Fourier transform of this periodic function with period 2 to the lambda. In the quadratic case, this function has a very nice product representation according to the binary expansion. And from this product representation, it's quite easy to get some upper bounds for this Fourier term, because if you consider two consecutive factors of this product, you get some saving, which is this easy lemma. So if this function 1 plus e of phi of x is defined by 1 plus e of x, and if you take this product phi of alpha minus x and phi of alpha minus 2x, then you get some saving. Of course, the trivial bound would be 4, but now if you have some alpha here, it's slightly below, slightly less. And if you apply this to this Fourier term, you immediately get an exponential decaying bound for this Fourier term. So it decays exponentially with this decay. And what has to be done then is to consider exponential sums of this form, where you, for example, take the binary sum of digits of the squares and consider this exponential sum. And you want to get a non-trivial bound for this exponential sum. For example, if you use this exponential bound for alpha equals 0 and alpha equals 1/2, then you immediately get that the digits related to a Morse sequence are evenly distributed. So 1 and 0 appear with asymptotic frequency 1/2. This just follows from this exponential bound in two lines. And what you need to get this exponential bound is to get an estimate of this form of the Fourier term. Well, this was observed by Mauduit and Rivard in their paper, and what they need is more or less analytic number theory, van der Corput inequality, and so on and so forth. It's quite technical, and you need estimates for quadratic exponential sums, so it's relatively basic but not easy. But the main ingredients that you need is this non-trivial bound for the Fourier part. What you can get very easily in this case, it's not trivial, by no means trivial. It's a long technical way to get these upper bounds, and I just can give you a very short and oversimplified version of the idea that Mauduit and Rivard developed there. So you consider this exponential sum and apply a van der Corput inequality to it. And of course, if you use the van der Corput inequality, you get differences in the exponent of this form. And now, if this r is relatively small, n plus r squared will be close to n squared. So this means that the discrete expansion of these two numbers will differ only in the first few digits and not on the higher digits, which means that this difference can be replaced by the restricted difference, because the higher digits will be the same of this and that. Not for all n, but for almost all n. There will be some exceptions, but you can estimate this number of exceptions. This means if you use this inequality, you can replace the binary sum of digits function by the restricted binary sum of digits function, which is now periodic. And then you apply a Fourier transform, and then you use the estimates on the Fourier transform to get some non-trivial bounds. So this does not really apply in this case. You will not get it, but I hope that you see the idea what is behind this analytic number theory that is used here, and why you have to use these Fourier terms and why you have to use these bounds to get them. For example, here you get a relatively large sum over h1 and h2 up to 2 to the lambda. And if you consider the case where h1 and h2 are both 0, which means that this exponential part is trivial then, so it's trivial, so the maximum value n. So you have to get some saving on the free part, and we have it here because we have a non-trivial exponential decay here, and so we get a non-trivial bound for this term. And you have to get bounds for all terms, of course, but this is another story. But here you see why you have to use this free part. If you want to prove more subtle theorems, for example, if you want to prove this result on the normality on the two amorphous sequence along the squares, you have to consider more difficult Fourier terms. So you have to not only to consider the sum of digits function or the restricted sum of digits function at one number, but along arithmetic progression of fixed length k. And the difference of this arithmetic progression is not restricted but can be arbitrarily large. And what you need is a non-trivial bound of the same form as before, so that you see an exponential decay on this bound. But in this case, it's very difficult to get, at least it was very difficult for us to get this kind of bound, whereas in the previous case it was almost not trivial, but it was very easy to get. Here it's quite complicated to get it. But it holds, and it holds also uniform in these differences. And you have a similar proposition as before. If you have this exponential decay, then with some work, and this some work is only very, very technical and takes many pages, you get a non-trivial estimate for the corresponding exponential sums, where you have the sum of digits function of n square, n plus 1 square, n plus 2 square, and so on. So you get the joint distribution, and this leads to the normality result. So this was only a very short, sidestep to the technical part. So finally, let me mention two background problems. So these problems, or the origin of these problems are from Gelfond's paper from '68, where he considered only the sum of digits functions along arithmetic progression. Nowadays, these are automatic sequences, known as automatic sequences, so it's very easy nowadays. But what was interesting is that he formulated three problems. The first problem was a problem where he considered two different bases. So, and he conjectured that you have two different bases that they behave independently, which is certainly true, or should be also true if you, for example, consider two automaton and a three automaton, and so it should be something, they should behave independent in some form. This was completely solved in '99 in the quantitative form. And non-quantitative form was given by Bézineau in the beginning of the 70s, I think, so quite early. The second conjecture is related to the primes. So you consider the subsequence of primes of the sum of digits function mod m. And I already mentioned that this second conjecture of Gelfond has been proved by Mauduit and Rivard. And the third conjecture was on polynomial subsequences of the sum of digits function. And here it was proved by the squares, again by Mauduit and Rivard, and it is half open for polynomials higher degree. We only could prove it for relatively large bases. So this is so the two-amorphic case is open for cubes, for example. So there is some progress, but it's not completed. So this is the precise statement. You have to assume that Q is relatively large, depending on D. This C is a D. So where D is the degree of the polynomial. So I think if the degree is 3, then it should be something about 700. So the Q has to be very large. There are some explicit bounds, but they are certainly wrong. So it should be true for all bases. But then we can prove uniform distribution results. And you can also do something else. you can also do, for example, to look on local results where you don't consider the sum of digits mod m, but the sum of digits function as it is. And here I want to state just one theorem that we proved together, namely an asymptotic formula for the number of primes, where the sum of digits function of these primes is a given number k. Of course, this is not an asymptotic formula that is valid for all k. The k has to be in the expected range. Of course, the sum of digits function has an expected size because it's a sum of digits. So the average digit is q minus 1 over 2. And so if you sum up to get an expected number of digits, so it has to be in the expected range, such that this asymptotics is significant. But for example, you can, if you take precisely this expected range, then you can, the corollary is that the number of primes up to 2 to the 2 to the k, such that the sum of digits function is k, is given by this precise expression. It's almost 2 to the 2k divided by a constant and k to the 3/2. So this is what you expect. And the second background is, of course, the Sana conjecture that I already mentioned. This is related to primes, and it is related to the minimal topological dynamical systems with zero topological entropy, where if you consider a sequence u to the of n, which is defined as f of t to the n, where t is the transform in the dynamic system applied to x, where x is any element of this set x, and such a sequence is also called deterministic if it comes from such a topological dynamic system with zero topological entropy. And in particular, if you have an automatic sequence, then it's deterministic. And if you consider also the dynamical system that is related to this automatic sequence, you take all the shifts and the closure, if you apply this to some element of this dynamical system, then this sequence is also deterministic. So, for example, if you take just the first element of the sequence, then it's just you just recover the automatic sequence, but you can start from any other initial point. And these are, so automatic sequences are special cases of these deterministic sequences in this context. And the Sana conjecture says that every deterministic bounded complex sequence that is obtained in this way is orthogonal to the Möbius function, which means that if you take this product with the Möbius function, that it has yet to get a non-trivial upper bound, so that there is some averaging along these products. And there are many cases where this has been observed, that it is true. So I don't go through this list. I am sure you know this much better than me. But what is the relation between the problem we discussed and the Sana conjecture? And this is the following. If we want to get some estimate of a function of a, say, automatic sequence, un along the prime, so if we average this was some exponential of the sequence, we have to study usually this sequence, this sum, where lambda of n as the von Mangold lambda function. And then we Baudy and Rivard apply the Warn's method to get to relate it to sums of type 1 and 2 and so on. So using analytic number theory to get non-trivial bounds for this, which imply non-trivial bounds for that. But the same method applies when you replace lambda of n by the Möbius function. And if you can do this, you can also do that by the same method. You can use the same estimates to get it. So if you can do this, you get also a method to prove a non-trivial bound for this, which implies, so this means that you can prove orthogonality of this sequence G of U of n and the Möbius function. Okay. And now I want to finally I want to present you some results on automatic sequence related to the Sana conjectures, which are very recent. The first one is relatively easy to get, but it uses a concept that seems to be important for the general case. We cannot do the general case at the moment, but it seems that we have a kind of strategy to handle automatic sequences. Not only the two-amorphous sequence, for the two-amorphous sequence everything is known, but the two-amorphous sequence is a very special automatic sequence. It turns out that most of the automata are so-called synchronizing. What does synchronizing mean? Synchronizing means that there is a so-called synchronizing word, W0. So here it's 0, 0, which means that if you apply this word to any state, so if, for example, if we apply 0, 0 to this state, we end up here. If we apply it to this state, we also end up here. And if we start here and apply 0, 0, we also end up in this state. So this word 0, 0 synchronizes the automaton to one specific state. So, and it turns out that almost all automata, even connected automata, this is a very recent result, are synchronizing. Okay. By the way, the two automata for the two-amorphous sequence and for the Rudin-Shapiro sequence are not synchronizing. So the interesting cases are the exceptional ones. It seems so. But the generic ones are synchronizing. And in a very recent result, together with Jean-Marc and Clemens Müllner, we proved that if you consider a synchronizing automaton and the automatic sequence that is generated by this automaton and the dynamical system that is generated by this automatic sequence. So there are two steps. So then every sequence that you can observe in this way from this dynamical system is orthogonal to the Möbius function. So the Sana conjecture holds for all these nice automata that are generic in some sense, but they don't cover the interesting cases. The proof is really very elementary, so it's a good exercise. So, but I think it's a new result, and it's really in some form easy if you look at it in the right way. You just look at the last occurrence of the synchronizing word of the input sequence, and then there is some tail, and this tail can be analyzed by considering residue classes, and you just apply Dirichlet's prime number theorem. Well, but there are some other instances that we can cover together with this notion of synchronizing automata. So just to give a few definitions, we call it automaton primitive if the corresponding matrix, the sum of the transition matrix, is primitive. So it's clear what it means. It's invertible if these transition matrices are invertible. So I already mentioned this kind of property. And I also need a reduction of an automaton, which means that you just regroup the states and you can find, so the easiest case is just to group all states to one case. This is a trivial reduction. Or you leave all states as they are. It's also a trivial reduction. There might be other reductions. It's clear what it means. And we define two types of automata. So the first automaton looks like this. You have non-trivial automorphism on the automaton. So for example, if you remember the automaton of the Rudin-Shapiro case, so it was just a mirror. of itself. So it has a non-trivial automorphism, and if you reduce it along this automorphism, so you just put these things together, the reduced automaton should be synchronizing. This is what we call type A. So this is just an ad hoc definition, but the root and Shapiro sequence is of type A. And another type is the following, that we assume that an automaton is type B if it's primitive, and if there exists an invertible reduction. So this is an automaton, this is the reduction. So this covers several states of the original automaton, so that the reduction is invertible, but one state of the reduction, which is a subset of states of all states in the original automaton, is synchronizing, so that if you consider, so there exists a word W0 that if applied to all of these states in the original automaton, then you end up in some state of the original automaton. So you combine in some way the definition of invertible and synchronizing. The Drmota sequence is of type B, for example. And it turns out that if an automaton is type A or B, then the corresponding automatic sequence is orthogonal to the Möbius function. So, well, our hope was that all automata are of type A and B, which is not true, unfortunately. It turns out, but anyway, all two automata, so with base 2, up to 4 states are of type A and B. So we cover some. So we are at the beginning. And the smallest automaton that we could find that is not of type A or B is this one. It has 5 states, so it's not synchronizing and so on. It has not, it's neither of type A or B, so it's something new. It's maybe an interesting one. We don't know. But it actually we could prove, so Clemens Müller more or less did it, that for this automaton, the corresponding automatic sequence is again orthogonal to the Möbius function. So it seems that you can modify this automaton according to the following construction, that you consider, so you cannot maybe, it's not, maybe you cannot synchronize the whole automaton, but it's maybe possible that you can define some subsets and that subword W0 where you can synchronize into this subset. So this subset is not maybe a singleton, but maybe a larger subset. And if you consider these subsets that where you can synchronize in some way, and then reduce the automaton according to the subsets, you get of course then a synchronized automaton. But of course you're losing information, and you have to recover this information in a different way. And it seems that we are not done with that, but it seems that with help of this idea that you reduce the automaton in this way and then try to recover the missing information by an invertible structure, that by using these two methods, the invertible structure and the synchronizing idea, that not in the basic form but in this form, that we hope that we can cover maybe not all, but many automata in this way to prove that the automatic sequences related to this automata are orthogonal to the Möbius function. Okay, thank you very much for your attention.